Hello, my name is Sina Sadegpour. I'm a senior researcher on the field of PMOTs at the University of Leuven in Belgium. In this presentation, I would like to introduce you some of our achievements on developing linear PMOT arrays for medical imaging. But what is a PMOT? PMOT stands for Piezoelectric Macromachine Ultrasound Transducer, and as the name explains, it is based on MEMS technology. A PMOT consists of a membrane that is placed on top of a silicon substrate. In this case, our membrane is also a silicon out of a SOI wafer. On top of a membrane, we have a piezoelectric layer which is sandwiched between the top and bottom electrode. When we apply an electric field around the piezoelectric layer by the electrodes, we induced an expansion or shrink in the piezoelectric layer, and because it is laterally clamped to the membrane and a strain or a stress laterally is induced in the piezoelectric layer, which results in bending the membrane, and this is how we can generate ultrasound wave by the PMOT. PMOTs, because of their unique characteristic, can be very useful for medical imaging applications. For example, PMOTs can be designed to have any resonance frequency from audible to gigahertz. PMOTs also help to accelerate the advent of handheld transducers because they can easily be integrated with CMOS technology because they have same nature based on silicon. They can be fabricated with a very low cost, and also they don't require any low actuation voltage or no DC bias as needed for a CMOS, and also they have a very high sensitivity. All of this simplifies the front-end electronic, and we can fit the whole front-end in a compact packaging of the handheld transducer. PMOS also help to perform 3D imaging much easier than before because they are based on lithography techniques, and we can have a more complex wirings and have access to all elements individually in a 2D array, which was very difficult before in conventional technologies. We can also have a multi-frequency design, which means that we can put several PMOS with different resonance frequency in a very small area to support basically different frequencies with a very wide bandwidth, as shown in this picture, which is one of our previous work based on aluminum nitride. But how a PMOT is fabricated? We start with a SOI wafer, then we deposit our bottom electrode or any other seed layer that is needed for the crystallization of the piezoelectric material. Then we deposit our piezoelectric material and we pattern it to access to the bottom electrode. Then we deposit our top electrode and we also pattern it to have access externally for wire bonding, for example. Then we cover everything with polyimide and pattern it to have access to the bottom electrode and top electrode. Polyimide is used first for the protection of everything to be used underwater, and also to damp the vibration of the membrane to widen the bandwidth. Then we realize the membrane but by a deep reactive ion etching process, which was followed by HF vapor phase etching to remove the box layer. During the design of a PMOT array, we have to consider several parameters such as azimuth and elevation beam pattern, pitch, and mechanical crosstalk. If we assume that we would like to design a linear array, we can put several PMOTs in a linear configuration with a certain pitch, which is the best to be half a wavelength in order to cover both for a phase array and a linear array if you have enough number of elements. But the problem is that the beam pattern, in this case, in the elevation direction is very wide. To solve this problem, we connect several PMOS in parallel in each channel in order to have a narrower beam pattern for the elevation. If you would like to focus the beam pattern in the elevation, we can either use a lens or we can use a semi-2D structure, which means that we have several groups of PMOS in each element, and we have access to them individually, and we can do kind of beam steering in the elevation. This is a technique that we also use in our PMOTs. Regarding the mechanical crosstalk, any kind of perturbation introduced in the transmission of the ultrasound wave through the substrate, silicon substrate, can reduce the mechanical crosstalk. For example, such a design that each element is randomly oriented with respect to each other, or if each PMOT does not have a symmetrical shape, we can also place each PMOT randomly placed and oriented with respect to other PMOTs. To introduce perturbation. We have fabricated several linear arrays with 128 elements with the different frequencies of 1.5, 2, and 6 MHz and different pitches of 96 up to 214 micrometer. We use PZT as our piezoelectric layer, which was deposited with Sol-Gel process. This SEM image shows the crystalline structure and columnar structure of the piezoelectric material through its thickness. This image is a microscopic image of a PMOT array with 1.5 MHz resonance frequency. Each PMOT in the array has a diameter of 160 micrometer with a pitch of 214 micrometer. Each element in the array is individually wire bonded to a PCB. We insist to have wire bonding because this is a very cheap and reliable technique of packaging. And this is a final image of the arrays placed on the PCB, and in this side we can have access to each element individually by coaxial cables. We performed several experiments to characterize our PMOTs. In air we use laser Doppler vibrometer, and underwater we either use a hydrophone to characterize the transmission or a commercial transducer to characterize the receive responses. We also performed an underwater pulse echo experiments while the reflected signal were measured individually through coaxial cables for all channels. The 1.5 MHz PMOT transducer shows an in-air resonance frequency of 2.35 MHz with a response of 30 nanometer per volt, while all PMOTs in one channel were excited at the same time. The underwater frequency response shows a 118% minus 3 dB bandwidth with respect to the center frequency and a minus 6 dB bandwidth of 184%. The time domain response are illustrated in these figures. This is the transmission response to 1 cycle square wave and to 4 cycle square waves. And this is the receive response. The blue one shows the transmitted signal from our commercial transducer, and this one shows the received signal by one of the channels in our PMOT array. The reflection is also recorded. The transmit response of our PMOT array per channel is 430 Pascal per volt at 3 centimeters, and the received response is 190 millivolt per megapascal. This table shows the characteristic results of our 6 MHz PMOT with also 128 element and a pitch of 0.2 millimeter. The velocity response measured by the LDV is 134 millimeter per square volt at 8 MHz in air. The transmission sensitivity is more than our 1.5 MHz PMOT, and it is the electrical impedance at the working frequency is 13 ohm, and the input electrical capacitance per each element is 1.8 nanofarad. We performed an imaging experiment with our 1.5 MHz PMOT array. In this experiment, we used these measurement setups in which we used 4 metal rods, 2 of which with diameter of 7.5 millimeter and the other 2 with a diameter of 5 millimeters. We submerged our PMOT and placed in front of the metal reflectors, and all elements of the array are connected individually to our acquisition systems by coaxial wires. In this experiment, we used single line transmission method with a focus point at 60 millimeter, and we scanned an area of 90 degrees with a depth of 12 centimeters. As you can see, the reflectors are illustrated clearly with a good spatial resolution. We also perform an imaging experiment with our 6 MHz transducer, but in this case we use different reflector configuration in which we use different reflectors with different thicknesses placed in a mold in front of the transducers. The thicknesses are 0.5 millimeter, 1, 2, and 3 millimeters. We also use similar single line transmission method of imaging with a focus point at 60 millimeter, and we scan an area of 90 degrees wide and 12 centimeters deep. This is the scan results in which the bright points are the signals recorded from the reflectors, and the red dots